let us finish this lecture with a few consequences of the Kakutani Theorem, and maybe we should start with a small observation about the differences between compact let me do it like this, compact spaces in the case of the metric spaces and general topological spaces. So I will put here like this a remark. And we will put it like this: E for a metric space XD, X is compact even only if every sequence in X has a convergent subsequence. And in the case, which is actually not true in the case of topological space, for a topological or topological space, and now I write it now X, and this will be topological space T. There exists compact. So maybe I should say, if X is compact, maybe that's a better, compact. If X is compact, it is possible in general that a sequence in X may not have a convergent subsequence. And C, in addition, if X tau topological space is such that every sequence in X has a convergent subsequence, is not readable, has a convergent subsequence, this may not apply, but this doesn't imply that X is compact. So let me begin with the first observation, and this observation is the following. So we'll write it down theorem because it's kind of important, but that's just simply a corollary of Kakutani theorem, and it says the following: let E be a reflexive Banach space and L contained in E a closed subspace, then L as a Banach space is also a reflexive Banach space. And the proof is quite immediate. So notice that the induced from sigma E star, that the topology induced on EL coincides with the weak topology. That means you can take this one as independently L star. Indeed, in order to notice it, you can just do the following. So take the space L and consider it first as take the topology on E star, and this one is E, and of course restricted to L. So this is my topology on that space, and take this one and consider it with the weak topology like here, and then take the identity operator and then take here functional f that goes to R such that f belongs to the L star, and then look what do I get here. And immediately it can be figured out that if you have a such functional, then by Hahn-Banach theorem, there exists an extension tilde belonging to L, means this time is on the whole space E, such that f tilde restricted to L is equal to f, and that means this will be your f tilde restricted to L. So that means it is actually the functional from the functional generating topology, that means on whole E. And similarly, you do the same thing in the reverse order, so that means now take this sigma L, and this will be L star here, and the other one is the induced, that means this is sigma E star, and take on L, so I just mark it here again, this is F, this is again identity, and take here F, and this F restricted to L, F restricted to L, where F belongs to the E star, so this goes here, so now you are getting connection, you are getting F restricted to L. Of course, F restricted to L belongs to the L star, so this is again continuous. So we are getting here these two topology are continuous. Identity in this case is this required homomorphism. So what should I do now? Just simply notice that since E is reflexive, by Kakutani theorem, we have that the unit ball, closed unit ball, is compact in sigma E star topology. This is compact. And if this is compact, so what else do I have? And since the ball in L, so put it like this, this is the set of all x belonging to L, such that x is smaller equal than 1, and we have here BL is equal to B intersection with L. So what do I have here? This is L is a closed subspace. Closed subspace is a convex set, so convex closed set, so this means this is a closed in sigma E star topology, and that one is compact, so we are getting this one is the set BL is closed in sigma L star. But since this one is a closed, E star, and since BL is a closed subset of a compact set, be in this one, in this topology. That means this implies that BL itself is compact, but you can now use the fact that these two topologies coincide in sigma L star topology. Again, by Kakutani Theorem, other direction, we get that L is reflexive. L is reflexive. Okay, so let's write another, so we prove it. So let's prove another, last one. Corollary, which we'll write also as a theorem. And this will allow us to identify the reflexive spaces. So theorem. Let E be a Banach space. Then we have E is reflexive if and only if E star is reflexive. Start with the proof. So we'll prove it. We need to show that basically you have that basically for every, so that means the duality map, we need to show the duality map, call this duality map, I put it like this, J with star, because it goes from the star to the E double star, triple star. Sorry, it means simply that if you take J star of F, so that means this will be a functional, on that one going to R, so that means this J double star of F on psi will be equal psi on F, so for psi belonging E to the star. So that means we need to show that every element for every element, and I put here psi belonging to E triple star, there exists F belonging to E star such that for every psi belonging to E double star, we have here psi on psi is equal to, and this will be just simply psi on F. Interesting, good. So let's do it. Okay, take psi belonging to triple thing, and consider the functional. And I denote this functional F. I put it like this. Functional F, and this will be on X. This is a linear function. It will be equal, and I just put it like this. This will be psi applied on J of X. So that one belongs to the E double star, and since this is clearly composition with the, this means that F is basically nothing else than the composition of J and Psi. Not Psi. This is wrong. Sorry. Okay, I made very bad notation. So this is Psi, not Psi. Psi. So please change it, because I use the E triple star is Psi, E double star is Psi, E single star is F. Keep it like this. So this will be Psi. Psi, and I put here J of X. So that's my correction. So now, of course, you can see that what is this? F actually is nothing else than J composed with Psi. This is continuous, so that means belongs to the E star. So I have that guy. So once I have it, so let's write it down. I also have that, I can write it down, that for every x belonging to E, I have here that this, I put here like this, psi of J of X. I have it, this will be equal the same as J of X on F, and that one, is this true? Look. Yeah. Is it? Check it. Why not? Okay, so let's say like this. This is exactly. Yes. Okay. No problem. So that means J of X on F. Let's check it. So what is this? So this is the same as F is composed. Sorry. So this is J of X, and sorry. Oh. Okay. So that means this is the same as F on X, and that one is F is nothing else than just simply psi in J on X. So this one is equal to psi of J of X, and 10. Yeah, that's the same thing. So we can basically use this notation, and you can write it down. This is that for every x belonging to E, that means J of X is equal to Jx on F, and since and since J is surjective, I can say like this. I can use this substitution. J of X is equal to Xi, where Xi is an arbitrary element in double star because it's surjective, it's reflexive. So what do I get here? I'm getting here that again, for every Xi belonging to E double star, I'm getting here that psi Xi is equal to Xi on F, and that's exactly what we needed to prove. So star follows. So we did it. So now we can just go other ways. So suppose that E star is reflexive. Then, by previous, that means this implications that we already proved, we have that E double star is reflexive. And if the E double star is reflexive, so we also have, and we have here the J of E is closed subspace. Closed subspace of doubles. Yeah, because J is an isometry, so it maps into, okay? Can identify it actually, E with that one. So this is the same as E. It's a closed subspace, but by previous theorem, before one, every closed subspace of a reflexive space is reflexive, but since, maybe I don't need since, but every closed subspace of a reflexive space is reflexive, we get that E, which is exactly equal to J of E, is reflexive. And of course, once it is reflexive, we know it will be surjective too. And that's it. So, I'm planning to do some problems, additional problems in additional, let's say, I try to spare some time next week and put some problems and solutions as some kind of examples to indicate to you how to deal with the problems dealing with the weak topologies and reflexivity. So up to now, let's say, I hope to finish one more topic in this chapter of the Brezis book, and then we will basically move forward to the uniformly convex spaces. So thank you for now. Thank you, and now let me stop it.